that I do at my company, and then dive into some concepts of big data and AI, and then go into more depth with some data and analysis, and finish it up with some set of references. So people in my line of work would probably understand what I mean when we work with a lot of charts and data. For each chart and data, we need to actually set individual thresholds and limits, as well as alerts for each one. And it gets a little out of hand pretty quickly, because while we are doing many things at the same time, we're also asked to keep an eye out for things that are being monitored. So to go in a little deeper about the monitoring systems that I do. First, we have our in-house system, where it was built as an internal tool, 40,000 lines of Python code, and it lists all the assets that we have added to our network. For DNS, which is a domain name systems, we have 2 systems to monitor that. If an IP is found to be unhealthy, we will remove it out of rotation, so that we can continue to do other things while we don't break service. These 2 systems monitor things that are more specific, things like CPU, GPU, RAM, hard drives, and other components. This will give us a more clear picture of things when things go down. These kinds of alerts, when they do come, are piped through chat channels, such as these 3 that we see here. We do that to also maintain a history as well as how things were worked on over time. Smoke ping specifically sends ping packets simply to see if servers are up and down, but also to more precisely see the quality of its ping reactions. One point that I want to note about smoke ping is the kind of smoke stuff that you see here. The distinction here is, for example, if smoke ping sends, like, say, 10 packets to a server and gets 10 pings back, the solid color that you see here is the median. So in 10 pings, that would be the 5th packet that they'll show. And if the other packets come in at different times, then they'll show up in more grayish areas known here as smoke. The Grafana is a nice tool that aggregates all the testing and charts that we have from other sources. So Grafana doesn't monitor things specifically on its own, but indirectly it imports the data from other places. And as you can see with all of these refreshes, it takes a while to reload all of them because it's a very graphically intensive application. And we prefer to use this so that we don't have to switch between all these different browsers and tabs to keep track of all these things at the same time. Oh, okay, so back. So now that I've run through all these tools, one point to write home is that we have an exceedingly increased amount of graphs to look at because of how big our networks get and how many things we have to look at. But we don't have time to look at all of this because we are DevOps, right? So what most people do is they will set a threshold and an alert that will fire off, which will alert us to come and take a look at it when things do happen, and then we'll go off and do something else. But it is included in our job description to monitor things, right? So we don't have an extra eyeball that we can take out of our eye and just set things. So perhaps maybe we can leverage AI to do this kind of work for us. So now I'm going to dive into some concepts, because before we can really use AI, we'll have to understand where we're coming from. Big data. What is big data? It is essentially anything that is greater than a number or a word. It could be a picture. A picture is worth 1,000 words. It could be media, sound, audio bytes, metadata, anything that contains quite a lot of bulk, and we're working with many units of such things to make our inferences. What is AI, which stands for artificial intelligence? Admittedly, it has gotten a bad rap as of late. People are wondering if we're building the next Skynet. But it's really not that scary or anything. AI is really the concept of the attempt to mimic human thoughts and functions. So on the right, you're going to see actual individual cells, human brain cells, which they make connections with each other, but we have memory. And as these connections grow stronger with repeated learning curves, these connections become stronger. And we try to emulate that structure actually, as we can see here on the left, which is what we call a neural network. Each particular round spot is also called a neuron, and the connections to each other, we actually call those weights. So after 2001, we have gotten out of this word called neural networks, and we started calling these things deep neural networks, specifically because we added layers between the input and output layers. This allows us to make more connections and record more pattern recognitions in the metadata and big data that we are seeing here. Another thing to note is that all of the connections between the neurons are already pre-made. When you're looking at an organic human brain, the cells don't connect to each other until learning is done. But given how artificial intelligence is designed, all of these connections are already created and mapped out. So how do these systems that already have these connections actually record things? Well, this is really like a skeleton blueprint, and the actual memory is made by giving values to each connection, which we would call weights. So a couple things that I want to explain here. If these were organic cells, then we would actually see like a circuit. They could connect, and they could actually connect back to earlier layers to complete a circuit. But in AI systems, the memory only goes in one direction, in this case from the left to the right. The input layer is on the left, the output layer is on the right. And they're making their connections in one direction as opposed to any direction that biological systems can. So that's one thing to note, that is a difference. And so aside from weights, there's also something called bias, which is seen in the colored circles on the right. And basically these would fire downstream only when they get enough of push from neurons upstream. And so every single dot will come with a number for each weight, which is known as the lines here. And the thicker the line is, the higher the weight value. And then the bias is also an integer value given to each circle. So this is an example of an actual AI engine at work. This picture is flipped on its side, but it can show you that this is an example of them making inferences of relationships between different blobs and parts of a particular picture. And so the solid lines you see here are the connections they're making to each other when they're making that particular identification in this case. And Caffe is the engine created by Berkeley AI Research, known here truncated as BEAR. Caffe is superseded by Caffe 2. So here we are using Caffe to look at smoking data, and you can see in this example, each neuron is going to take this piece of chart and look at it slightly from different angles, different colors, different exposures, and just to see if we could get more patterns out of them, and if we could find the same sort of patterns in the future pictures that we look at. All of this is used to find points of interest, which we would call beat boxes or bounding boxes right here. Caffe is just one of many different AI programs that you can use. We chose Caffe specifically because of its strengths in vision processing, as well as with Python. And NVIDIA got into the game, and they really helped us to make advances and make all this possible because they have taken a lot of these algorithms and put them on SoCs or system on chips. So putting things into hardware allows us to do a lot more computations and quickly. The caveat here is that you're going to need an NVIDIA GPU. Here we purchased a Quadro P1000, the graph you could see here, the chip you see here on the right. And Digits is really a GUI, a graphical user interface that we have in front of Caffe. And NVIDIA created this so that you could be more point and click with these things instead of doing everything on the command line. Of course, Digits can be a front end not just for the Caffe engine, it could also be done for the TensorFlow from Google or for Torch. It could be used as a front end for many of these different parts. So the pipeline that we tried to implement at my company is like this. So to explain, we would take the picture data, feed that all and organize it in a database, and then feed all of these repeatedly through many iterations through a neural network in order for them to form their weights and biases and connections and find patterns between each data point. Once it's done learning, we'll take it over to production and have a Python script slide the data, big data, out of the smoke ping and take these charts and present it to the AI and see if the AI can confirm any points of interest. One thing I would note here is that while Docker containing the AI, when the AI is at work, it cannot take the results that it got and improve its inference and decision making with the new data. If you want the AI to take the new data and improve its intelligence, you're going to have to take the new data and bring it back to the environment here on the left and retrain it so that it can do it. So that's one thing, at least for AI for picture detection, it can't learn and do work at the same time, which is why we have to separate separate environments, and the left one definitely needs the GPU to do its training. Another caveat to report is that when you want to feed these data in for learning, you will have to manually draw boxes around points of interest so that the AI knows what you're looking for. Up on the upper right is a link to one such tool. It creates a text file known as written in kitty format. That's capital K-I-T-T-I. Not sure what that stands for, but kitty format is basically written in a text file that needs to be in the same file name as the picture and put in a separate folder. And on the upper right, you can see that it has the values for the locations of the boxes and whatnot. This is a more teased out description of what each column stands for, but I want to bring attention to the don't care red box. Basically, in the box of interest here, you can draw a smaller box inside called don't care so that it can leave out false positives. So initially, we see here 300, the data went through the AI 300 times, and the certain peaks that you see here are times when they think that they found meaningful patterns between these pictures, and they can use those towards new pictures that come along. Now, since I'm starting from scratch, and given how much data and how fast this thing can do, it can potentially take weeks for it to train up to a usable model. So I also included in the next slide an example of one that is fully trained, which can probably detect things with pretty high accuracy in the 0.8 and 0.9. This example was taken from other projects that I see online that are already well trained for their field. In this case, these are graphs that typically represent them demonstrating recognition of cats, dogs, cars, and pedestrians. Probably also pushed and funded by companies that are interested in car detection for driving. But taking those pre-formed AIs of weights and whatnot, and using that to look for smoke ping data is a pretty hard stretch. So we are going to need some help to help build this kind of ability up to a higher level. And this is done on various open source networks, on GitHub and other places and whatnot. And so in the spirit of helping each other, pass around with data we're permitted to pass around AIs and help increase the recognition, I've included the setup that I have here, which people can reference later from my slides. And one thing to note for this setup, for other people who want to do this, is I'm not just running a regular Docker command here. I'm running NVIDIA Docker. You need to run NVIDIA Docker so that when the container starts, it can find the GPUs on your computer and mount them correctly into the container for use. Otherwise, it won't run well at all. So here's the citations on the research I did. And that's it. Thank you.
Okay. Thank you, Mr. Patrick. Okay, questions? Okay.
Yeah, so the question here is, given that the model takes weeks to train, what do you view as the return on investment? It's operations, there's usually a cost associated.
Yeah, that's
Okay.
exactly why the initial groups that that trained it to look at cats or dogs just to demonstrate its ability, and the ones that did training on cars and pedestrians, this is exactly why I mentioned there are organizations out there that have funded and helped produce that made this into a useful form. In fact, when I checked, those guys, when they made the model work that well, it went through around 1.5 to 2.5 million iterations. That's like they ran the data through the AI millions of times to find these meaningful patterns. And so we're starting from scratch here. So really what I'm saying is the ROI will increase the more that we combine our work online. And let's say I train my AI up to a certain level with my data, and you have slightly different data, and you train off your data. And if we get like 10 to 20 people all flipping the AI around on GitHub, then we would get it up to the points of standards that we see up there. Yeah. We're going to need everybody's help on that list.
Okay, so thank you very much.
Thanks.
Sharon, let's invite the CEO of DevOps Institute, Jane Groh, to make a presentation about